We're on page 99, and 99 is continuation of what we saw on page 98, except that we're going to do other examples using radicals. So we've got problems, example 5, 6, 7, and then we've got the distance formula and the application of the distance formula in number 8, an example 8. So let's get started with example 5. We've got to simplify this, the square root of 7 times the square root of 7. Now because the index is the same, we can multiply 7 times 7 and get the square root of 49, and the square root of 49 is 7. Or we can just say this is root 7 times root 7, which gives us 7. So it doesn't really matter which way you use it. Now here we have a plus sign between the two terms. So we have a sort of an a plus b, a minus b kind of problem, because this is a and this is b. So we have a plus b and a minus b. And so when we do that, there's a difference of squares and there's no middle term, because the plus ba is canceled by the minus ba. The inner and the outer term cancel each other. So it's really the first times the first, which is root 7 times root 7, which is 7, and the last times the last, which is root 3 times root 3 with a minus in front of it. So we get 7 minus 3 equals 4. Now what I did do here was to show the outer term, which is minus root 7 times root 3, and the inner term is plus root 3 times root 7. So these two terms are just the one is negative, one is positive, and they cancel each other. So the outer and the inner cancel each other, and you're just left with the first term squared minus the last term squared, which is 7 minus 3, and that gives you 4. Now if we go to 6a, we discussed this. You can see that root 3 over root 7 is really generic form x over root a. And what we do is multiply. We take the x over the root a and multiply the top and bottom by root a. And this is really 1, so we're not changing anything, because root a over root a is 1. So when I multiply the top and bottom by root a, I'm not really, and the bottom by root a, I'm not changing anything. So here we have 3 over root 7. Remember, the objective here is to get rid of the root sign on the bottom. Okay, rationalize means that you're going to get the rationalize the denominator in order that you eliminate it. So now here I've got root 7 here. We're going to multiply the top and bottom of the original fraction by root 7. This doesn't change anything. Root 7 times root 7 gives me 7, and 3 root 7 gives me 3 root 7 here. So this is the answer here. And you'll notice this one does not have a root sign on the denominator. In part B, it's a different kind of problem, because we have a positive sign between two parts, both which in this case have a root sign. So what we do is we multiply the top and bottom by the conjugate of this, which means we just take this and change the sign to minus. And so we multiply the top by root 7 minus root 3 and the bottom by root 7 minus root 3, and we're not changing anything because this thing in the red bracket is essentially 1. So we're not changing anything. So when we multiply the top, here's what we get, and the bottom is a squared minus b squared, and so root 7 times root 7 gives me 7, and plus root 3 times minus root 3 gives me minus 3. So 7 minus 3 is 4. The 2 goes into the 4 2 times, so I divide the 2 into the 4 here, and I get 2, and I'm left with root 7 minus root 3 over 2. So in 6b, we multiply the numerator and denominator by the conjugate. If you go back to page 97, you can see here you wanted to simplify this. You rewrite it, and then you multiply by the conjugate, which is right here. And that gives you x root a minus root b. And again, here, when you multiply this one by this one, you get the first term squared, which is a. Root a times root a gives you a, plus root b times minus root b gives you minus b. So there's no more root sign on the denominator. So what we're doing is applying these rules that we learned on page 97. In the first case, there's no sign on the denominator between two terms. There's only one term, so we simply multiply the top and bottom by whatever is at this position. Here we have two terms with a plus sign in between, and we multiply by the conjugate. Now we're going to look at problem number 7. And problem number 7, before we do that, we're going to go back to the notes on page 97. And we reviewed this, that if we have a to the 1 over n, this means the nth root of a. So we've got to be able to go from this to that, or from, in other words, from left to right. Or if we have this, we have to be able to go back to this. So for example, if I write 1 over 2 here, where n is 2, then this means that I'm looking for the square root of a. I put a 3 here, that means I'm looking for the cube root of a. If I have a 4 here, it means I'm looking for the 4th root of a. And similarly, if I have the 4th root of a, which means the 4th root of a to the 1, this is a to the 1 over 4, raised to the power 1 over 4. The other rule is that if we have a to the power m over n, we can break this into two parts, a to the 1 over n, which is really this part over here, you can see. So this part here becomes that over here, right here, which is just a substitution of this. And then we have m here, which is this m here, which becomes this n here. But the key thing to realize is that a to the 1 over n is the nth root of a. So you have to be able to go from the left to the right, or from the right to the left in doing these problems. So problem number A, I've got 9 to the 3 halves, and I can break this down into 9 to 1 half times 3, because 3 times 1 half gives me 3 halves. Now the reason I do this is 9 to the 1 halves is the square root of 9. The square root of 9 is 3, and then because of this 3, I've got 3 cubed, and I got 27. So essentially what we're doing is applying these rules here, and you can see this is 3 halves, and this is a, then the half becomes here, and the 3 goes here. The half goes here, and so what we're doing is moving from here to here. So that's part A. In part B, we've got minus a to the 2 cubed, and again, we're going to break this down, and instead of 2/3, we're going to write this as minus 8 to the 1/3. Okay, because of this 3 here, I'm going to go from here to here. 2/3, and I'm going to do 1/3 and 2 here. 1/3, and 2 here. So all I'm doing is going from here to here. Now, the -8 to the 1/3 is the cube root of 8. And the cube root of 8 is -2. But then I've got to square it, so I get 4. Now I've done this over here in a little more detail. I wrote -8 to the 2/3. And now instead of writing -8, I'm going to write -2 cubed to the 2/3. Now what happens is this 3 cancels with this 3, and I've got -2 squared, which is 4. So this is just a different way of looking at it. Instead of writing -8, I wrote -2 cubed. Now I multiply these two together, so what happens is this is in the numerator and in the power term, and this is in the denominator. So I cancel the 3 here and the 3 here, and I'm left with a 2. I get 4 here. Now let's go to part C. Very simple. If I have 3 to the 4/3 times 3 to the 8/3, I can just add the powers here. So I can add the 4/3 to the 8/3, which is what I'm doing here. 4/3 plus 8/3 is 12/3. I just add the numerators here. Divide by the 3. 12 over 3 is 4. 3 to the 4th is 81. Why is that the case? 3 to the 4th means multiply 3 by itself 4 times. So 3 times 3 times 3 times 3 is 81. Think about it. 3 squared is 9. 3 cubed is 27. And 3 to the 4th is 81. Now the last one, again, can be done in different ways. But you can see here that you have 9x to the 3/2, x to the 5/2, and x to the 1/2. So what we can do is remove the 9 from the brackets and apply the 3/2, because this is 9 to the 1. 9 to the 1 times 3/2 is 9 to the 3/2. X to the 1 times 3/2 is x to the 3/2. Then we have x to the 5/2 here, and on the denominator, x to the 1/2. Now, instead of writing 9 to the 3/2 right here, I'm going to write 9 to the 1/2 times 3 here, because 3 times 1/2 gives me the 3/2. So I'm breaking this up. I'm essentially going back to this part, this rule here, where 9 to the 3/2 is written as 9 to the 1/2 times 3. And that's, I'm going from here to here in applying, going from here to here. And now what happens is how do I get x to the 8/2? Well, I add 3 plus 5. 3/2 plus 5/2 gives me x to the 8/2, and this is x to the 1/2. So I broke this part into this. I added the 3/2 plus the 5/2 gives me 8/2. When I multiply these two together, I add the powers. Now what happens is square root of 9 is 3. That's why there's a 3 here. This cubed is that cubed over there. Now when I'm dividing here x to the 8/2 by x to the 1/2, I bring this 1/2 up and subtract it. You may remember the rule x to the a over x to the b is x to the a minus b. So here I take the 1/2, bring it up, change the sign, so I get 8/2 minus 1/2, which is 7/2. 3 cubed is 27. Now I've done this problem a little differently over here. So here we have 9x to the 3/2, x to the 5/2, x to the 1/2. Instead of 9, I wrote 3 squared. x to the 3/2, x to the 5/2, x to the 1/2. So the only thing that I did here was change the 9 into the 3 squared. That's the only thing. Now what I'm going to do is apply the 3/2 to this term, which gives me 3 squared to the 3/2. I'm going to multiply this times this term. I get this. And then I'm going to take x to the 1 and multiply it by 3/2, and I get x to the 3/2. This term stays exactly the same here, and this term stays exactly the same here. Now these two, the 2 on the numerator here and the 2 on the denominator here, cancel each other, so I'm left with 3 cubed. Don't forget that this is 2 over 1. So if it's 2 over 1, this is on the numerator, that's on the denominator. They cancel, and I'm left with 3 cubed. Still have the x to the 3/2, still have x to the 5/2, and x to the 1/2. So I'm going to leave the 3 cubed as 3 cubed, and now I'm going to add x to the 3/2 plus 5/2, 3 plus 5, 3/2 plus 5/2. I'm going to bring this up, and it's minus 1/2. 3 cubed is 27. 3 plus 5 is 8, minus 1 is 7 over 2. So I get exactly the same answer that I got over here. It's just a slightly different way of doing it. Usually these problems can be done in more than one way. Now here, in problem number 8, we want the distance between the points -2, -1, and 4, 7. And the distance formula is equal to the square root of x2 minus x1 plus y2 minus 1, where x1 and y1 represent the first ordered pair, and x2, y2 represent the second ordered pair. So you imagine you have 2 points on a line. The ordered pair describing this one is x1, y1. The ordered pair describing this is x2, y2. What's the distance between them? That's what we're trying to do. We're trying to calculate the distance, and the distance is given by the square root of the difference of x's plus the difference of the square root of sign, and these are all the in the square root sign. Now, you can call this x1 and this y1 and this x2 and y2 if you want, or you can call this one x2, y2 and this one x1, y1. It doesn't matter which you identify as which, because when you square them, the signs come out, and so it doesn't matter which. Now in this particular case, you can see x2 is 4, so here's your x2, 4 minus 2, 4 minus 2 right here. Your difference in your y's is 7 minus 1, because there's a minus here, so it's minus, and then you've got the minus 1. So 7 minus 1. 4 minus 2 is 4 plus 2. 6 squared here is 36. So you go 4 plus 2, that's your 6 squared. 7 minus 1 is 7 plus 1. The minus 1 here becomes plus 1. 7 plus 1 is 8. You got 8 squared. 6 squared is 36. 8 squared is 64. 36 plus 64 equals the square root of 100. The square root of 100 is 10. So let's go over this again. What we're asked to do, the reason this example is coming in here is because we've got the square root sign. This is the distance formula. Distance formula looks for the distance between this point and that point. And it's obtained, d is the distance, by substituting, taking the difference in the x's and the difference in the y's. The difference in the x's squared and adding them to the difference in the y squared. As I said, it doesn't matter what you call x1, y1, and x2, y2. It doesn't matter what you can call this x2, y2, and this one x1, y1. It'll still work out. You can't say this is x2 and y1 though. You have, if this is x1, this has to be y1. If this is x2, this has to be y2. The numbers have to go together for the ordered pair here, right here. So you can see that. So this completes our discussion of page 99.